lab report guideline, I already posted the lab manual as well in the eCampus. So this lab manual includes three experiments. So the first experiment is a single component study using PBT simulator. That's a CO2 phase behavior. And then we'll do the experiment number two, which is the saturation pressure of a binary system. And then at the end, we will have the lab number three, which is the study of the experiment three, a study of the multi-component systems. So today, what you need to do is to go over our lab number one. So there is an introduction, and then there's a discussion on the PBT lab simulator, which basically tells you the assumptions. For example, here it says the Peng-Robinson equation of a state is used for this to calculate the phase behavior. And you know from our discussion what is the Peng-Robinson equation of a state. That was the most famous equation of a state we use in the oil and gas industry. And what are the assumptions? For example, Peng-Robinson equation of a state doesn't consider still considers all the collisions are perfectly elastic. Okay, so it doesn't consider the energy loss when you are mixing different components. So these assumptions you need to mention that. So you need to go over it, and then and these are the keywords that I'm going to use performing the PBT lab simulator. And it starts from here actually, where it says a single component study using the PBT lab simulator. This is the process that I'm going to follow, and then you can basically use it for your lab report. Okay, and then we'll have our lab number two. So today we are going to cover all the way till page number 6. Okay. So the lab today, as I said, the title of the lab is a single component study of the CO2 using PBT simulator. So we are going to study the CO2 phase behavior. Okay. So again, the motivation is as a reservoir engineer routinely working with the data obtained from the PBT studies, we need to know what this information is, where the information is coming from, and how this information has been obtained. Because if you don't know, you're just taking the sample, sending it to the lab, and the lab comes back with some PBT analysis, and you don't know how they have measured these properties, basically you cannot have a good judgment on how to use that. Okay. So as I said, the experiment can be done either using the PBT lab simulator or using physical PBT apparatus. It did have the PBT apparatus that we were using before, like 3 years ago, but most of them were working with mercury, and then the state regulations prohibited using the mercury-driven instruments, so we get rid of those and we are using the PBT simulator. And hopefully by next year we will have a new PBT apparatus which are not working with the mercury. But for now we are going to use the PBT simulators. PBT simulator is even better, because when I was a student and I was using PBT apparatus, it was taking us like 3-4 hours to just do one experiment, one step of the one experiment. So it was like very frustrating, very time consuming, and you have to just split the time, and doing it during the weekend, and it was a headache. But with this PBT simulator, it's very easy, and any operation that you can do with the PBT apparatus, you can do it with this PBT simulator, so it's exactly the same. However, this is more quick, this is much faster, and it doesn't have any risk. As I said, in the other PBT apparatus was working with the mercury, and we were always, working with mercury. If the pump breaks, the mercury spills and all those, nasty stuff. So we are not doing that anymore. And then here you are allowed to do the mistake. So what happens if you do a mistake? Let's say you forgot to open a valve of the pump and you start pumping. So what it does, the software says boom. So it goes red, and then you have to start all over. But if you do it in the lab and the pump goes boom, then there's lots of problem. You have to clean, and then you cannot continue the lab, and so many headaches. So here is much easier, faster, and safer. Okay. So as I said, this PBT simulator is using the Peng-Robinson equation of state as a basis, and for the discussions, you need to refer to our chapter 2 and chapter 3 of the book. Okay. So here, what I have is in the left is the actual PVT apparatus, and in the right is what the PVT lab simulator that we are using is look like. So as you can see, it's exactly the same as the actual apparatus. Here, basically, you have the cabinets and you have different gas tanks. Here you have the visual cell that you put your actual fluid, and you use these gas tanks to add components if you need it. So in lab number 3, we'll see that. And then you have this LC pump. Basically, we use the LC pump to shake the cell to make faster to system to go to the equilibrium condition. We have some servo pumps that we can set, what rate I want to inject, how much I want to inject. I have hand pump as well. That's, I can just use it to inject or remove mercury. This gray color is actually mercury and the brown is liquid. So anything brown in this software represents liquid. Anything yellow represents gas, and the gray represents the mercury. So we are going to use mercury to compress or to expand the liquid. We are assuming the mercury is incompressible. We are assuming when we inject, let's say 10 cc's or 1 cc's of mercury, or when we withdraw 1 cc's of mercury from the visual cell, these pipelines, they don't take any volume. Okay, so the exact number will be applied. And we have the pressure gauges. So all these blue boxes are pressure gauges. As I said, the brown represents liquid. These are showing the volume of the liquid and volume of the gas. We have 2 density meters, one to measure the density of gas, one to measure the density of liquid. We have centrifuge, we have the gas chromatograph, which I'll go over it, when we use those. So this software is perfectly similar to what you will actually see in the lab. We have some temperatures. We have the oven temperature, which basically shows the temperature of the fluid in the cell, and the ambient temperature, which is the ambient temperature of the lab. So this is the whole setup that we are going to use for this lab. There are some keys, the F keys that we are using for operations, okay, that I'll tell you. For example, if you press F2, you can operate the valves. If I press F2 and then I put 08, enter, if the valve is closed, it makes the valve open, and if it's open, it closes the valve. So anytime I want to work with the valves, I press F2. And then I put the number of the valve, and then I press enter. If I want to use the servo pump, I use F3. If I want to use the hand pump, I use F5. So if I press F5, then I activate the hand pump. Then I need to say how much I want to inject mercury or how much I want to remove mercury. If I put minus, it means I want to remove mercury from the cell. If I put plus, it means I want to inject mercury to the cell, okay? So this is for the F5. F3 operates the servo pump. F6 operates the LC pumps to shake. So for single component, we are not going to use it, but for the multi-component, every time you change the volume of the cell by adding or removing the mercury, you must shake the cell. Otherwise, your reading would be wrong, okay? So, and then we use F10. F10 is a gas chromatograph, which basically tells you what is the composition of the gas or liquid inside the visual cell. So that's for that. And then the rest of the keywords we will use it later on in the next lab number 2 or lab number 3. Then I'll go over it when we get there. Assumptions, as I said, the thermodynamic equilibrium is instantaneous. Just assume the Joule-Thomson effect is neglected, mercury is incompressible, and the tubing doesn't take any volume. So, as I said, the single component study would be the objective of this lab. We are going to measure the bubble point pressure and the point pressure of the pure carbon dioxide, okay? So we usually do this in 4 different temperatures, but here we are just going to do it on one single temperature, okay? And then we are going to collect the data points and then plot the pressure versus volume diagram. So if you remember the pressure versus volume diagram of the pure components, as we plot the pressure versus any type of volume, like total volume, normalized volume of the fluid, remember the pressure is the pressure of the fluid, the volume is the volume of the fluid, not the mercury that we are injecting. And then we start from the point where the system is in liquid. We remove the mercury, we expand the liquid till the pressure drops and we see the first gas bubble. That's our bubble point. And then we continue till we get the dew point, and then we get some points in the dew point. So we are going to recover one of these lines. And then when we have that, we will make some observation, which if the bubble point stays equal to dew point, stays equal to vapor pressure as we are performing this experiment or not. Okay, and that's about it. So the pressure volume diagram of the pure CO2 that we are going to perform the experiment. Okay, so in the next part, I'll actually start with the PBT lab simulator, and we are going to do the experiment.